Okay, there were some homework problems that had to do with the Kohler Mugiano stuff. First was 2003, Control 2, question 4 and 5. They're all very similar. Okay, if you have a regular solution with several components, the excess Gibbs energy is given by this equation here. This is the omega 1,2 is the binary parameter for the 1,2 system, and that's the energy of the 1,2 bonds minus the average energy of the 1,1,1,2,2 bonds, the same thing, and you're assuming that all the binary bond energies hold in the multi-component system and they're constant and so on. Okay, where the only calculate an expression for the partial property of component 1. So you've got to differentiate the thing. Alright, so this was, okay, the way to, where's my medicine here? I have another cold. Sick all the way. Anyway, this is the safest way to do it. Your G, this is your molar little g, excess molar Gibbs energy. This is per mole of solution. So the extensive big G is the total number of moles times the molar energy. Don't forget that. Okay, big G. This is joules per mole, this is joules. Is the total number of moles times the molar Gibbs energy. You got to do this. So it's N total, TOT means total. So N total is just the sum of all the number of moles times the molar. And G excess of 1 is the derivative of the extensive G excess, not the intensive, but the extensive with respect to N1, keeping all the others constant. So these are the main expressions you've got to use. The rest after that is just mathematics. You have an expression for the molar excess property. You have to write the extensive property, not per mole, but total, which is N total times the molar property. And then G excess of 1 is the partial of G excess with respect to N1, keeping N2 and so on constant. Okay, so now I'm making and of course you can always write that X1, the mole fraction of 1, is N1 over N total, and so on for all the mole fractions. Okay, so these are all the same thing. You just got to be careful with mistakes. So the integral, so X1, X2 is then N1, N2 over N total squared multiplied by N total. Okay, so X1, X2 is N1, N2 over N total squared and multiplied by N total. Same thing for all of them. So the excess Gibbs energy of component 1, you take the partial with respect to this, keeping N2 as a constant. It's a partial derivative. So this is in parts, this would be N2 over N total, and then the derivative of 1 over N total with respect to N1 is minus 1 over N total squared. Same thing for all the rest of them. All right. And if you do the mathematics, you'll end up with an expression like this. So the G excess of 1 is 1 minus X1 times blah, 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 blah for all the binary systems that contain component 1, 1, 2, 1, 3, 1, 4, etc. And for all the systems that do not contain component 1, it's just minus the, something like that. Okay, so once again, the important things are, don't forget to put the N total here before you do it, otherwise you'll come out totally wrong. Okay, and you differentiate by parts, and derivative of 1 over N total, which is N1 plus N2 plus N3, is minus 1 over N total squared, and so on. Okay, let's just look what this stuff means. Let's look at ternary system 1, 2, 3 and do this. So G excess of component 1 is going to be 1 minus X1 times X2 omega 1, 2 plus X3 omega 1, 3. That's kind of okay. It kind of varies across here. Minus omega 2, 3 X2, X3. So it's this term here that I'm interested in. So this indicates, let's suppose that omega 2, 3 is negative. So let's say omega 2, 3 is negative. then omega 2,3 is negative because in the excess Gibbs energy of mixing, and the 2,3 binary system has negative deviations from ideality. But this gives you then a positive contribution to GXS1 in the ternary system. Or if omega 2,3 is positive, that means 2 and 3 tend to demix in the binary system, and this then gives you a negative contribution to GXS1. So there's this minus sign here. How do the 2,3 interactions are affecting the activity of component 1, as you were. This is the RT log gamma of component 1, and that's being affected by the 2,3 interactions. So RT log gamma 1, activity coefficient of component 1, is clearly affected by the 1, 2 and the 1, 3 interactions, which vary between the binary systems, but it's also affected by the 2, 3 interactions with a negative sign. So if the 2, 3 interactions are negative, this gives you a positive contribution to RT log gamma 1 and vice versa. So explain that to your grandmother. Why the negative sign?
If 2, 3 have a tendency to demix and they don't interact with each other, they have more probability of interacting with 1 to show that they really make a connection.
Yeah.
There's less interaction, basically there's less interaction between 2 and 3, so there's more interaction between 1 and 2 and 1 and 3.
No, if a 1's next to a 2 or a 1's next to the 3, it's going to have the same energy whether or not the 2 and 3 are interacting. No, that's not the reason.
Okay.
Has to do with this. The GXS of 1 is the rate of change of GXS as you add N1. So as I'm starting here, let's say I started a 2, 3 binary system. Let's suppose this is whatever. Suppose they're negative. Okay, so the 2 and 3 are strongly interacting. It's giving you negative deviations. I now move along here, so I add. That's what I'm doing. I'm adding GXS N1, keeping N2 and N3 constant, basically. What I'm doing now is I'm diluting the solution. I'm reducing the number of 2, 3 interactions because this in the binary system, you have only 2s and 3s. Remember, it's randomly mixed. You have 2s and 3s. Now as you add 1, you're diluting it. The number of 2, 3 interactions is decreasing. So the number of negative 2, 3 interactions is decreasing. So this gives you a positive. dg dx SDN1 is positive. Okay, you're reducing the number of these very strong interactions by adding a dilutant. Or the other way, if 2, 3 interactions are positive, then it's giving you a negative contribution. You're removing a lot of the positive. So you have to kind of think of what all this means in terms of, so this is kind of a little surprising. You have 2, 3 interactions are negative, and this GXS1 then gives a positive contribution. You're diluting the thing, diluting it and removing the negative interaction. Okay, so you should be sure that I'm not going to go through all the mathematics, but you should assure yourselves that you know how to do partial derivations. Question 5, very similar. Okay, you have a binary solution, ternary solution with two regular binaries, AB and AC are regular, and the binary solution BC is subregular. Subregular means you have a linear term as well as the constant term. Write an expression for the integral excess Gibbs energy of the ABC system using the Kohler approximation. Alright, so our Kohler approximation is constant along Kohler approximation goes this way. Alright, so we will go to the Kohler approximation 5 over here. This is very straightforward then. So GXS is alpha. So well, the AB system is regular, so it's just alpha, not AB. The CA system is also regular, so it's alpha AC. The BC system is subregular, so it's alpha BC plus this was ABC, so you're basing it on this point here. It's alpha naught plus alpha prime BC, and this term here then has to be kept constant along this line. So XB plus XC is constant here in the binary system, and then as you go along here, you're dividing by XB plus XC. Okay, so the binary term is XC minus XB. So you will go into the ternary along a line where B plus C is, the ratio of B over B plus C is constant. So C over C plus B and B over B plus C are constant along that line. So this factor here and this factor over here is constant along that line, which is what you count here. It's constant along that line, and it's equal to the binary value at this end. Okay, the next one was get rid of that. These answers are kind of mixed up. Okay, this was 2005, control 1, number 6. Where am I here? Doing the wrong one. It's too complicated. Alright, this is very similar. You have a ternary solution, ABC. The binary properties are given by this down here. Again, these two are regular, and this one is subregular, written as a normal power series rather than a Redlich-Kister. Use the Kohler model with A as asymmetric to write an expression for GXS and also GXS A. So we're going to use the Kohler model with A as the asymmetric term, so that is we're going to go across, we're going to base it on these 3 points here. This line here is XA is constant, and this line here is the ratio of BC is constant. Okay, where the two sides are regular and the base is a subregular solution given by that expression. So you want GXS and GXSA. Okay, so GXS, okay, once again, and well, in these two terms here, they're just regular solutions, so there's no problem. Sorry, yeah, it doesn't make any difference really, because they're, what you're using, Kohler or whatever, they're just constants. And then this is B plus B1, and then you're replacing in the binary, it would be XC, and you're XC over XB plus XC is constant along that line. So once again, for the partial property of A, we go to the same thing, the total number of moles. The total gives GXS is N total times molar GXS. You write the whole thing out, replacing XA by NA over NA plus NB, etc. Do the differentiation anyway. It's still, I mean, it's...
Question.
Yeah.
Why the NC over N plus NC, NB plus NC equal XC?
Show me what you're talking about. Here?
That
Here?
one,
Here?
yeah. No, the left one.
Here? It's NC over NB plus NC. That doesn't change. That's a constant.
No, why that's equal to XC but constant?
Oh,
Because
sorry.
NC over N total is XC.
Why is that, put that equal to that? That's a good question. That looks wrong, doesn't it? You're right, it should be XC over XB plus XC. This. Yeah, you're right, this should be XC over XB plus XC. Same down here, that should be BXB over, okay, yeah, you're right. That's only equal to XC in the binary system, not in the whole ternary system. All right. Because I use these. You're right, you're right. I don't know how that got missed. Okay. In 2005. These are all very similar. I don't know, maybe I didn't need to give you all of them. Number 5 to number 3. Okay, you have obtained optimized binary parameters for binary solutions in the ABC. It's using the Quasi-Chemical approximation. You then use a geometric technique to estimate the Gibbs energies in the ternary solutions. Okay, then you compare your calculated values for the partial excess Gibbs energy of component A with experimental data at several compositions in the ternary system. You find that the calculated values are slightly less negative than the experimental ones. Okay, so therefore you are the ternary solution. When you do your Kohler Approximation interpolation just from the binaries, you find that you're getting a little bit too negative. In other words, the ternary solution, the GXS of A, which has been measured, that you can now measure the partial property of A by vapor pressure or electrochemical cell, and you find that it's slightly less negative than what you expect. Okay, so your approximation is giving you a little too much negative deviations. Therefore, you add less negative than the experimental one, so you have to put in a little more negative deviations. So then you add a negative empirical ternary parameter, omega XA XB XC, with omega less than 0, to your expression in the ternary solution in order to stabilize the solution and decrease GXSA. Seems like a logical thing to do. You want to be a more negative deviation, so you're going to add a negative term. At ternary compositions where XA is small, you get the desired effect. However, when XA is relatively large, you discover to your horror and dismay that GXS of A has become less negative because you added that term. Okay, that is including the negative excess term has caused GXSA to increase. Okay, which is not what you wanted to do. So it would seem that by making adding a negative term to your excess Gibbs energy expression should make the whole thing more negative. It certainly makes GXS more negative, but the partial GXS of A is not more negative. It depends on composition. So what's going on? So okay, that was it, 2002 question 3. So I'm just looking at this extra term. I'm just looking at the ternary term. The binary terms are whatever you want. This is just the additional contribution due to that ternary term. Okay, so GXSA is dG dNA is ddNA. Then the big G multiplied by the total number of moles, and so on. So get this is XAXBXC is NaNBNC over N total cubed. And to get from little g to big G, I've multiplied again by dNA plus N plus NC. I go through the partial differentiation with respect to Na, and I end up with GXSA giving me that expression. And what you find out then, if XA is small, omega, let's say omega is negative. So if XA is small, then this term is in fact negative. But if 2XA is greater than 1, or if XA is greater than 0.5, this term becomes negative and the whole thing switches sign. So in other words, that's not the greatest ternary term to be adding. Okay? Like, it doesn't do what you really want it to do. You want a ternary term that's going to bring the whole surface down, but it's also going to bring down the partial properties as well. So, I mean, you got to be careful. You put in a negative term for GXS, and at large values of XA, it's going to actually increase your GXS. Because this really doesn't have a tremendous amount of physical significance, and that's just the way the mathematics work out. It's generally not what you're after.
Excuse me, can we do the same thing considering the XA, XB, and plus x, does it work? Means if we also consider xa, xb plus xa, xc in the g-axis.
You mean you make a different, you have a different function here?
Yeah.
Yeah, well, there's ways of doing that, I'll be showing you. You mean don't use xa, xb, xc, but use a different function?
No, I mean that in the g-axis, you only consider the ternary term.
Well, the binary terms are all, it's linear, the binary terms are all
Yeah.
independent. I'm only talking about the effect of this term.
Yeah, I know, but I mean, if we do the calculation considering the binary term too,
Yeah.
does it work?
No, it's still the ternary, no, the binary terms, you start with the binary terms, and then you're adding a ternary term in order to change it.
Yes.
So this ternary term is not, there's no interaction between the binary and the ternary term. No, you'll still get this extra term. You get all your binary terms plus this. If I write out all the binary
Yes.
terms plus this, and I then calculate gxs of a, I'll get all the binary
Yes.
stuff
And,
plus this term.
Is
So
it-
this term is not doing what I want it to do. I'm not sure. Here I have gxs equals binary terms
Yeah,
plus this.
yeah.
Down here I'll have gxsa equals binary terms plus this. The binary terms will be the same as if you didn't include this. Then this gives you this extra effect.
Yeah, because I did the calculation with the binary terms, and then I assumed that, okay, if xa is small, so 1 minus xa is equal to, like, we can say it is equal to 1, and I drop down some pairs and...
No, all I'm worried about is the effect of this term. The effect of adding this ternary term to your expression for gxs will add this ternary term to your expression for gxsa. If xa is small, it's going the right way, but if xa is big. So that kind of term, it shows it, it just kind of seem obvious. You put this in, it's negative, the whole lot it isn't. The reason is if you plot this curve along this line, let's say I go along this line here, from here to here. Okay, call that point X. I go along from point X to point A. And I plot that term. The term actually looks like this. It comes up with a negative. You're kind of hoping it would go like that. But it doesn't. It comes around and then it comes around like this, so that when you're on this side, the intercept is actually on the wrong side. Over here, sorry, the intercept is, yeah. No, sorry, the other way around. Comes like this. So if you're over here at low A, then your partial property of A, which is the intercept, is the same sign as the curve. But if you're over here, even though the curve is positive, your intercept over here, it comes around with an inflection point. It isn't you might expect it to be a constant second derivative, but it isn't. It comes around like that. So you can do that, but it's not the greatest thing to do for a ternary term. Okay, and the next was 2008. Two. Let's do 3. I can have this one in English if you want. Consider a ternary liquid solution, A, B, C, in a one sublattice. The binary solutions are subregular. So all binary solutions are subregular, expressed using a Redlich-Kister model. Using Muggiano-Tup approximation with A as asymmetric components, give the excess and the excess of A. So we're using Muggiano-Tup. So Muggiano-Tup with A as the asymmetric component means you're doing a parallel line here and then a perpendicular here. So this is a line of XA equals constant, and this is a line where XB minus XC equals constant. Okay, so you have your Kohler, your Muggiano, your Redlich-Kister model for all three binary subregular. got the answer for that. Okay, so your g-axis then is, so as you go for the g-axis of AB, you want it to be constant along that line. Okay, so here you have a term XA minus XB, but to have XA constant, you replace XA minus XB by XA minus 1 minus XA. And along this line here is the same thing. In the BC, in the binary system, it was, AC. The binary system, it was A2 plus B2 times XA minus XC. In the AC binary, you replace XA by XA, and you replace XC by 1 minus XA, so that this term and this term here, these two functions remain constant along that line. For the BC, in the binary, it's XC minus XB, and along this line, XB minus XC is constant, so you just leave that as it is. And that gives you your GXS in the Kohler tube model. So for the AB and the AC terms, you replace XA minus XB by XA minus 1 minus XA, or 2XA minus 1. And so this term, and this term here, 2XA minus 1, is constant along that line, and it's equal to XA minus XB at this end, which is what you want. And this term here is constant along this line. And if you're doing DJXSA, it's the same thing as DGDNA. And sorry, then this should be DNA plus MD plus NC times GXS. I mixed up there. This is the total number of moles times the little g excess DNA. So same thing. GXS of A is big G DNA is DN total times little g, which should be there. DNA, let NA plus NB plus NC equals N total. XI is NI over N total. Do the differentiation. And if I haven't made a mistake, I come up with something like that. This has been put up on the server as well. If you find any mistakes in it, let me know. But I mean, this is just kind of the mathematics. The most important thing is don't forget to put the N total up here. And don't forget the equation, and don't forget how to do partial differentiation. Okay, so all this is done internally, of course, in FactSage, given the partial properties. Okay, so any questions? Anyway, you'll find all of these answers on the server, so you can check them all out. Okay, we started on last week on short range order. Quickly reviewing, when you have short range order, the tendency is for your heat of mixing to have like more or less two straight lines and then come down to a fairly sharp V, negative V, and for your entropy of mixing to go through a minimum around the composition of maximum short range order. So one way of modeling this in a binary system, so we went through some examples. One way to do this was the associate model, where the associate model you assume a model in which you have one sublattice, and on that one sublattice you can have A's, you can have B's, or you can have AB molecules. And they're randomly distributed over the sites. Okay, so you have an entropy of mixing, which is an entropy of mixing simply of the A's, the B's, and the AB's. And the heat of mixing is the fraction of AB's times the energy of forming the AB's, which is the energy for that reaction. And so you have an equilibrium constant. And as I showed, when you solve that thing for different values of omega, you do in fact get a nice, when it's negative, you do in fact get a nice negative heat. And you do find for negative values of omega, you do find that your entropies are going down negative. You do have a little problem here though, I didn't talk about this enough yesterday, so I'm going to talk about it now, is what happens for only slightly negative values of omega associate, you actually end up with an entropy that is more positive than the ideal value, which doesn't seem right. Let's look back at this to see the reason. The reason is, let us suppose that omega is equal to 0. So the energy for this reaction is 0. Okay, so omega, actually if you consider omega to be the Gibbs energy, omega is like delta G0. Here I've only put it as a heat term. It's the enthalpy, but you could have an excess entropy, you can have a non-configure entropy part of it as well. You could have omega AS as A minus BT. Okay, equals delta G naught for that reaction. In this case, I've simply assumed that the B term is small compared to the A term. Okay. Omega, I took that to be the heat of the reaction. You could take it to be the Gibbs energy of the reaction, so that this is the enthalpy, and that's the non-configurational entropy of the reaction. Okay, and that's equal to minus RT log K for the reaction. And then K is for that reaction, it's the mole fraction of AB associates over the mole fraction of A times the mole fraction of unassociated B. So you see what you've got here is exactly like a gas. You've got exactly like a gas. You're saying, if this were a gas, you have A, B, and you have AB molecules. You have a delta G naught for the reaction. A plus B forms AB. Minus RT log K, the equilibrium constant, would give you the partial pressure or the mole fraction of the species AB over the... Okay, it's exactly, you're treating the liquid or solid like a gas. Okay, you've got A's, B's, and AB's, which are randomly distributed. You have an energy of forming the AB's, which is the Gibbs energy of forming the AB's is minus RT log K. K gives you the ratio and the mole fractions, and it's a gas model. Okay. Everybody good? Question? All right, so what happens in the gas model when delta G naught is equal to 0? When delta G naught equals 0, K is not 0, K is equal to 1. And in that case, the mole fraction of AB is by no means 0. So in other words, when omega is equal to 0, this does not reduce to the ideal solution model. If you want an ideal solution model, the ideal solution model, you just have A and B and no AB. But in this model, how do you get that? What you might expect naively then, that if I made omega, which is the delta G naught for that reaction, equal to 0, I would reduce to the ideal solution, but I don't. K is equal to 1, I still have a large number of XABs, and that in fact is why the entropy is high, because now you have A's, B's, and AB's. You've got more different kinds of particles to mix. You've increased the entropy of the material. Okay, as I say, looking at a gas, just imagine you had a gas, and over here you had, say, sulfur, and here you had oxygen, and here you had SO2. The heat would look like this. If you mix sulfur and oxygen to get SO2, you're going to get a negative heat coming down more or less as straight lines. And your entropy also is going to go down like this, because on this side, on the left side, you would have mainly sulfur and SO2, and on the right side, over here, you'd have mainly oxygen and SO2. It's exactly like the gas model. Okay, so when omega equals 0, the K is equal to 1, and you have a large number, still have quite a few XAVs around, and that is the reason that as you start to make the negative, you actually end up increasing the entropy of the thing. Only as you then go to more negative, then it starts to come back down again. How do I get the associate model to reduce, and what limit does the associate model reduce to the ideal solution model? Only when omega is equal to plus infinity. If the energy of forming the AB pairs is infinite, then of course they don't form. So but this isn't really what you want to happen in your model. So your model, the associate model can model the binary systems okay, as long as you have quite negative values of the formation energy for the associates, but it does not reduce to the ideal random mixing model, and it's really no good at all for positive deviations. The positive deviations, of course, would be the other thing. A's and B's tend to stay apart from each other, and of course this isn't going to express that at all. Okay. Now, so, that's why I don't like the associate, that's one of the reasons I don't like the associate model. So I say don't use the associate model, but unless you have some good reason to believe that your liquid really does contain molecules. I mean, if your liquid really, for some reason, contains AB and AB molecules, well then, yeah, this is what you should be doing. You know, but I mean, most liquids that people treat with the associate model, there's absolutely no evidence whatsoever that they consist of molecules. They consist of just preferential nearest pairs. Okay, let's then go on to the, oh sorry, then I was going to have you some homework problem, which was actually 17, 16. This is just to do it. For liquid indium antimony alloys, Jordan's proposed, well, he was one of the first, this is way back when he proposed the associate model. So basically it's the associate model. You have indium, you have antimony, and you have INSB molecules. You have a delta H of association, which is your omega. And I said just work the thing out. Well, I've basically done that for you on the slide, but I worked it out this way. I did it per mole. I did it per mole of overall solution. X antimony and X indium are the overall component fractions. Nothing to do with the structure, just you're mixing antimony and indium and that's what you mix. Okay, and the sum's 1, so I'm doing it for 1 mole of components. The heat of mixing then is equal to the number of INSB associates times the energy of forming them. The entropy of mixing then is the mole fraction of the associates times ln mole fraction of the associates plus mole fraction of, these are the number of moles of unassociated indium. This is not the total indium, this is the amount of indium that's left after the associates are formed. And the mole fraction of unassociated antimony times ln times n total, because I want this to be the total entropy, big S. Where n total now is the number of species, the number of associates plus the number of unassociated indium and antimony atoms. And so the number of moles of indium then, the number of moles of unassociated indium is the mole fraction of indium that you started with minus the number of moles of indium antimony molecules that you formed. And the number of moles of unassociated antimony is the starting antimony minus the number of moles of complexes you formed. And the total number of moles, if you just put these together, is 1 minus that. Just adding those two up. So then, in order to find the expression, I find what is the number of moles of molecules at equilibrium when the system reaches an internal equilibrium. This is an internal equilibrium within the single solution. The value is given by d delta G mixing the indium antimony equals 0. Okay, so I'm going to set the derivative of delta G with respect to the number of moles of complexes must equal to 0, and that gives you the minimum point. So I then put in the heat of mixing. This is the heat of mixing, and this was the entropy of mixing, and I differentiate them. And when you work it all out, you end up with what you had before. The amount of moles. You have an equilibrium constant, which is the number of moles of complexes over the mole fraction of complexes over the mole fractions of the unassociated indium and antimony, which is e to the minus delta H. So it's like a gas. Okay, so then we went on to the quasi-chemical model. The quasi-chemical model also tries to express short-range ordering, but the model is quite different now from the associate model. You don't talk about molecules. You have one sublattice. The lattices are occupied by A's and B's, but the distribution is not random. This is an AA pair, this is an AB pair, this is a BB pair, and you have pair exchange interactions. So if your energy, this is your quasi-chemical reaction. It's not chemical, chemical, because these are pairs. They're not molecules. They're not atoms. But you have an energy for this omega quasi-chemical. I've written it here where I said, okay, omega quasi-chemical is an A minus BT. In this slide, I'd let the B term, the non-configurational entropy, be 0, so the omega quasi-chemical is just the enthalpy term, but you could, of course, have a temperature dependence to it if you wanted. So essentially, the omega quasi-chemical is the delta G0 for this quasi-chemical reaction. This is your quasi-chemical mass balance, which we talked about. This is the number of bonds emanating from an A, and that has to be twice the number of AA bonds plus the number of AB bonds, and so on. So this is a mass balance, but it's a quasi-chemical mass balance, not a chemical mass balance. Number of pairs. The pairs are randomly distributed over pair sites. So while I went through this, I said you want to distribute them over pair sites, so it's XAA log XAA plus XBB log XBB plus XAB, etc., etc. So you should just have XAA log XAA plus XBB log XBB plus XAB log XAB, not the other terms, and not the denominators. If you're just mixing them randomly over the pair sites, but then that overcalculates the entropy, because if this is an AA pair, then this obviously can't be a BB pair. So you've overcalculated it. So what we did was we then divide each term here by the value in an ideal. You wanted this at least to reduce to an ideal solution in the limit. So in the limit of random mixing, XAA is XA squared, XBB is XB squared, XAB is 2XAXB. So in the limit of a random solution, this first term would be 0, and then I add in the ideal mixing entropy. So by putting in the denominators here and adding this term, I assure that del S configuration is equal to the ideal entropy of mixing in the limit of an ideal solution. But that is an approximation. Okay, but I say that this is mathematically exact in one dimension. It is not an approximation for a one-dimensional lattice, which is a string of atoms, a necklace. It is exact. I'll show you that in a couple of minutes. And in 3 dimensions, it's approximate. Again, we do the heat of mixing as XAB over 2 times omega quasi-chemical model. The 2, I'll show you why that's there for in a minute. And then you do the same thing. You say dg, G would be delta H of the quasi-chemical model times the number of AB pairs minus T SXS, minus T delta S. That's the Gibbs energy mixing. Just as we did for the associate model, you write an expression for G of the solution is the enthalpy term is the enthalpy of forming the pairs times the number of pairs. Then you have the ideal entropy. You take dg, dn, number of pairs, equal to 0, and you do exactly the same thing. It's exactly the same as the calculation we just did a minute ago for the associate model. The only difference is you have this somewhat different expression for the entropy, and you have these mass balances, which are slightly different from the mass balances that you used in the associate model. But when you work it all through, you end up with the same thing, an equilibrium constant. This is an equilibrium constant now for the quasi-chemical reaction, for this reaction. This is the number of AB pairs, this is the fraction of AA pairs, and the fraction of BB pairs. But now, let's look at this equation. Now, remember the problem I just said that you have for the associate model is that when your omega, your energy, your delta G naught for forming the associates is 0, this thing does not reduce to the ideal solution. The only way to get an ideal solution is to send your omega equal to infinity. Okay, but let's assume here now, let's assume that omega quasi-chemical model, if omega quasi-chemical model equals 0, okay, so if we have if I set this omega quasi-chemical model equal to 0, then I think you can see that you have, well, then you're going to have an ideal mixture, a random mixture. But omega quasi-chemical model is 0, XAB equals 2XAXB, XAA equals XA squared, XBB equals XB squared. Okay, you plug that into here. Okay, so therefore XAB squared over XAA XBB, if you make these substitutions into there, you end up with 4. Okay, XAB is 2XAXB. You make those. This is if it's an ideal solution, then the probability of an AB bond is 2XAXB. Okay. For an ideal solution, the probability of an AA bond is XA squared. You make those substitutions into this equilibrium constant. Comes out to be 4, which is what you get, because if omega quasi-chemical model is 0, the exponential here term is 1. So it comes out to be 4. So in the limit now, you're getting it right when the omega quasi-chemical model is 0. Okay, when there is no, when the energy for preferentially forming the AB pairs is 0, then the thing becomes an ideal solution. Unlike the associate model. Now you can go the other way. Now you can have an omega quasi-chemical model which is positive. And if it's positive, then this reaction is shifted, the equilibrium constant here is shifted to the left, and you have more AA and BB pairs in an ideal solution, and you have less AB. Okay, so you can go to the other extreme. If omega quasi-chemical model is negative, you tend to have associate pairs. So in other words, in the lattice, you'd have AB, AB, AB. If omega quasi-chemical model becomes positive, the A's tend to segregate and the B's tend to segregate. If omega quasi-chemical model is 0, you get an ideal solution. That's the reason we have a 4 here, by the way. So this goes up. Okay, so this is what you want, what I want. And you get almost the same, the graphs look almost identical when you have very negative, the heat of mixing looks almost identical when you have a negative omega. This is negative omega. The entropy terms, however, look very similar to the associate model when you have very negative. But as I just said, when you get less than very negative, they don't go positive. And when it's 0, you get a. I'll talk about positive omegas in a couple of minutes. Okay, so the limit comes in correct here. Okay, what do I? Well, I did just. There's an error here which I pointed out yesterday too, but this equation should have a Z over 2. Should be minus ZR over 2. Okay, because it's a total. You're distributing the pairs, the XA, ABB, and AB pairs over the pair sites. And if you have 1 mole of solution, 1 mole of A plus B, you have Z over 2 moles of actual bonds. Okay, so what did I say? This expression is mathematically exact in 1 dimension, approximate in 3 dimensions. I'll go into this a little bit more later. This is one problem. This is quasi-chemical model. It's not that the concept. The reason we're using a approximate expression for the configurational entropy, not because the model is approximate here, but it's because we cannot write the mathematics of it. We're trying to take a lattice with A's and B's. We have a certain number of AA and BB and AB pairs, and we're trying to distribute the pair sites randomly over the pairs randomly over the pair sites. And the mathematics of that is extraordinarily complicated. In 2 dimensions, in 3 dimensions, no one has solved the problem. In 1 dimension, it's quite trivial, as I'll show you later. So this is an approximation, but it's a mathematical approximation which is forced on us not because the quasi-chemical model physically has this error. That this is not an error in the model physically, it's a model in the fact that we can't figure out the mathematics. If we did know the equation for the for the randomly distributing the pairs, then we could write an exact entropy expression. You might want to say, why is it exact for Z equals 2, and this is a constructive. I've shown here that when omega equals 0, this reduces to the ideal solution. But let's suppose that omega, quasi-chemical model, equals minus infinity. In other words, it's strongly pushed to the right as possible. What should you get then for your entropy? In that case, your entropy should go like this. Okay, because when you're exactly at AB, you should have nothing but AB pairs. Okay, so if omega quasi-chemical is minus infinity, Then you want omega AB, you want entropy to be 0 at 50%. Correct? But if you put that into this expression, okay, what do you get in this expression then? So let's assume that XA equals XB equals 0.5. I'm doing this in the limit now of minus infinity. If XA equals XB equals 0.5, the fraction of AA's is 0, the fraction of BB's is 0, and the fraction of AB's is 1 at this point. Okay, so when you take a mole fraction of A is equal to B, omega quasi-chemical model is minus infinity, then you have nothing, you have no AA pairs, no BB pairs, you only have AB pairs. Okay, so let's calculate out the delta S then from this expression. And once again, there's supposed to be a bloody Z over 2 in front of this thing. So it's minus R Z over 2. The first term will be 0 because XAA is 0. Second term will be 0 because XBB is 0. The third term will be 1 times log of 1 over 2 XAXB. So this will be minus log of 2 XAXB, which is 1/2 times 1/2, if I haven't made a mistake, minus R 1/2 log 1/2 times 2, right? So don't forget, I made a mistake. It's Z over 2, that's 0, that's 0, that's 1, that's 1, that's 1 over 2 times 1/2. Negative, I put the halves up top, minus R 1/2 log 1/2 times 2. So, okay, I think. And let's work this out now. So this then is equal to R Z over 2 log of 1/2 minus 2 minus R log 1/2. And so you can see that this is 0 if in fact Z equals 2. Okay, so if I have an infinite quasi-chemical model is minus infinity, and you're taking it at 50%, what you want is that XA is X equals XB is 1/2. You want there to be only AB pairs. Okay, so just make these substitutions. Make these substitutions for the mole fractions into this equation, not forgetting the Z over 2 in front of the first term, but not the second term. Okay, make all the substitutions, collect terms, and you end up with this expression, which you see will be 0 when Z is 2, but only when Z is 2. If Z is greater than 2, I probably made a mistake. I think I got a sign wrong. This is correct, I made a sign wrong, haven't I?
Minus
Minus
2.
one whole term will be 0.
It's minus RZ over 2, so this is log of 2, 1/2, 1/2, but I put it up on the other side, so that's negative. Minus 2 R 1/2 log 1/2, because I have 2 1/2 log 1/2 terms. So this is RZ over 2 log of 1/2. And this is minus R log of 1/2.
In the parentheses, you have minus.
No, I think it's right. I think that's correct. Okay. So when Z equals 2, that's 0, but if Z is greater than 2, then this first term is bigger than the second term, but if these are negative terms, so what happens is delta S then is negative. Okay, so for Z, when omega quasi-chemical model equals 0, this is what you get for Z equals 2. But if you had, say, for example, Z equals 6, then you would get a term that looks like that. You still get your minimum here, but you're actually getting a negative configurational entropy. Okay, which isn't correct. Okay. So this is a problem, what you get if Z is greater, so this is Z is greater, Z can't be less than 2. And here you've got if Z is greater than 2, Z is greater than 2, and you got a very negative omega quasi-chemical model, it goes down to slightly negative values, which is physically not correct. But this isn't because, as I said, of an error in the concept of the quasi-chemical model. It's an error due to the fact that we're making a mathematical approximation. Okay, I'm going into great detail of the quasi-chemical model because I know you're all using it in your research. Okay, is everybody kind of cool with that? Okay, so on we go. There we go. Why don't we go on? Frozen. Why doesn't this work? Okay. As I said, I'm presenting all this. This is a talk I gave some time ago at CalFad. This is presented in a somewhat non-rigorous fashion because I'm trying to show you the most important points. And then later on we'll talk about all the details of the model. For example, here I'm talking only about constant omegas. I mean, as you know, you can make omega function of composition. I'm just talking about the general concept here. So we'll do this all again a little more rigorously later. The quasi-chemical model with Z is 2 tends to give delta H and delta S functions with minima which are too sharp. Associate model also has this problem. So this is experimentally noticed. When I say too sharp, I mean with respect to what you observe. So if we take, as I say, most of the quasi-chemical model gives you a heat of mixing curve which has a very sharp minimum. The actual heat of mixing curve, this is a quasi-chemical model. The experimental tends to come down here, but then tends to be a little bit more rounded at the bottom. Doesn't come down to such a sharp peak. These tend to be too sharp. Similarly, the excess the entropy quasi-chemical model tends to be a little too sharp here. It's never a point, but it's quite sharp, whereas the actual comes around like this and is a little bit more rounded. Okay, so it makes them too sharp. And the reason, which I really do believe this is true, and we started doing this later, like 2-3 years ago. We've been playing with the quasi-chemical model for some time, but we really only started doing it this way more recently. You have nearest neighbor interactions. That's where the short range order is what gives you the sharp peak. Okay, if you don't have short range order, then you get a parabolic regular solution type thing. Okay, so a parabolic regular solution. The sharp peaks in H and S, the sharp minimum peak, negative peaks, are because of the short range ordering in the first nearest neighbors. If you didn't have short range ordering, you get a more rounded peak. Now, we've only considered first nearest neighbors, but you know that there are also interactions between second, third, fourth, fifth nearest neighbors. They are not going to be highly ordered at short range. Further away you get, the interactions become less strong, and their tendency is simply to be. So you really have two terms. You have a quasi-chemical term here, which is really your first nearest neighbor ordering, and then you have the other terms for the remaining lattice interaction, second, third, and fourth nearest neighbors, could be possibly better modeled as a remaining lattice as a sort of a regular solution. So this is, if I were to go back in time and redo all our quasi-chemical stuff, I think this is a better way of doing it. I would use this term, I would have a quasi-chemical term, and then I would also include in my equation a Bragg-Williams term for the remaining interactions. And this term then tends to smooth it out. By putting everything onto first nearest neighbors, you're overestimating the short range order. The configurational entropy would then be the same as for the quasi-chemical model. We're still distributing the nearest neighbor pairs. And then I showed what you got here. This was a heat of mixing in the aluminum-scandium system. It tends to go down to peaks. If you take the quasi-chemical model, forget this for a minute. This is the quasi-chemical model here. This should be a little narrow here. This very sharp peak is the quasi-chemical model with omega Bragg-Williams equal to 0. Okay, so for this model here, you have only the quasi-chemical term. You don't have the Bragg-Williams term, and it's too sharp. If I put in a Bragg-Williams term with the Bragg-Williams over quasi-chemical is 2.5, or 1 or 2, if I start now, I make two terms, a Bragg-Williams and a quasi-chemical term with the ratio of 1. then it's more rounded in the middle. If I make it 2.5, it's even more rounded in the middle. So I can make this more rounded in the middle by making the Bragg-Williams term larger compared to the quasi-chemical term. And this seems to be a general rule. The entropy would go the same way. So if you make this term here 0, you get too sharp. The peak generally tends to be too sharp. And if you want to unsharpen the peak, you just make this, the ratio of this to this, progressively larger. The two of them seem to, they all converge in the limits as straight lines down here. It's the central part near the peak where you get a better fit if you add a Bragg-Williams term as well. Okay, and I really think this is because the Bragg-Williams term is taking account of the second, third, and fourth nearest neighbor interactions, which are not ordered. Well, they are somewhat ordered, but we're taking limiting cases here. We're saying the first nearest neighbors are ordered and the second, third, and fourth are not. So this was just a hypothetical thing we did. This was a solution AB at 1,000 degrees with constant parameters, omega Bragg-Williams, and the ratio shown. So this was omega Bragg-Williams over omega quasi-chemical equals 0. Then you get a very sharp peak. And then as you go to the Bragg-Williams limit, if the ratio is infinity, then you have only Bragg-Williams, and then you get a regular solution. Okay, so this first one here is almost two straight lines coming down to the minimum. The outer one is the x1, x2. Okay, so the ratio. And the entropy does the same thing then. So the same as the previous. The previous slide was this hypothetical solution AB, and this is the entropy that corresponds to it. So you see that if the Bragg-Williams term is 0, then you get a very sharp minimum here. And as you increase the ratio of the Bragg-Williams to the quasi-chemical, you get a less and less of a sharp minimum. And at the limit up here with infinity, where you have only the Bragg-Williams term, then you got this is your ideal entropy. Okay, so you can sharpen or unsharpen the peak using this ratio. This is kind of a good way to do it, I think. Okay, suppose you have the quasi-chemical model with Z is greater than 2. And omega Bragg-Williams is always equal to 0. Okay, so what we did is, let's go back here. What we were proposing in this paper really was, if we should have done this, we know that Z is not equal to 2 in a real solution. We know that Z is not equal to 2, Z is greater than 2. But mathematically, Z is 2 gives you the two limits right. It gives you the ideal mixing right when the omega quasi-chemical is 0, and it comes down to 0 here when it's equal to minus infinity. So even though we know that the Z equals 2 expression is, well, it's not a two-dimensional lattice, it's a mathematical approximation. It's a mathematical approximation that gives the correct entropy and the two limits, and it's probably going to be okay. But it gives a heat of mixing, which is an entropy which is much too sharp, the minimum. So if we're going to use Z equals 2, we should really be smoothing things out by adding in a Bragg-Williams term. However, another way of rounding it out is to have no Bragg-Williams term, but to let Z be greater than 2. So this is the same thing. Sorry, I'm confusing you here, but I mean, you're going to have to see this because this is what we've done. This is now, there's no Bragg-Williams term, but we're just using only the quasi-chemical model, but with different values of Z. And you can see it has almost exactly the same effect. When Z is 2, it's the same curve, and as Z gets larger and larger, the curve tends to get rounder and rounder. Okay, so this was the term for delta H for this hypothetical system, keeping Z equals 2 and just making more and more Bragg-Williams term, Bragg-Williams limit out here. In this equation, we have no Bragg-Williams term, there's only the quasi-chemical term, only the first nearest interactions are considered, but we're making Z progressively larger, and it has pretty much the same effect. And also in the entropy, it's going to have, well, okay, in the entropy, enthalpy, it's going to have more or less that effect. Why should that be the case? If you have Z is very large, Why is this happening physically again? I'm only Bragg-Williams. I'm only a quasi-chemical model. When I let Z become large, okay, when Z is large, let's go back to the equations, the ones that I did wrong. There's supposed to be a Z over 2 in here. When Z is large, you have a large number of pair sites. Okay, the entropy is given by just by distributing the the pairs over the sites where you can put the pairs. Okay, so although you have 1 mole of atoms, A and B, you have Z over 2 moles of pair sites. Okay, because every atom has Z bonds around it, so there's lots of places. If Z is equal to 12, then you have 6 places. If Z equals 12, you have 12 places around every central atom to put your bond. Okay, so the number, although the number of moles of A plus B remains 1, the number of moles of bonds, the number of moles of pairs becomes very large. Okay, so when the number of moles of pairs becomes very large, the system tries to have as many different, maximizes its entropy when it tries to have as many different kinds of pairs as possible. Or in other words, the pairs, the entropy term becomes much more important relative to the heat term. Okay, you still have this negative heat term, but you're trying to simply, the entropy term becomes more, because you have so many places to put the bonds, this entropy term becomes very important, very large. There's lots of places to put them. So if you, since you have 12, since Z is 12, you have 12 moles of, or 6 moles of bonds now, rather than 1 mole of bond, you have 6 moles of bonds. So there's 6 times as many places to put your atoms. Okay, so the entropy term becomes very important. It can really decrease its Gibbs energy by becoming random. Is that sort of clear? You're setting, the number of AB pairs is given by setting dg dNAB pairs equals to 0. It's always doing that. And this is then H minus TS is set to 0. So the system's always going to find the number, the way you find the number of moles of AB bonds is by minimizing dg dNAB. Okay, so now, however, this term here becomes very important. Okay, if you have a large number of AB bonds, you can get a really big entropy term here. Okay, if Z is equal to 50, then you got 25 moles of bonds. So this really becomes important. There's 25 moles of places to put your bonds now. Okay, so the entropy term dominates this minimization process here.
But the graph shows that change.
Sorry?
The previous graph shows the change.
Shows a what?
Change of entropy.
Previous graph, you mean this one? Yeah.
Z is changing.
Z is changing, so the entropy becomes more and more important. And it tends to...
Now entropy is changing.
Yeah, but it's going more towards... What I mean is as Z becomes larger, the system tends more towards a random mixture. NAB is a short-range order. As you increase NAB, you increase the short-range order. Increasing the short-range order always, by having more short-range order, in other words, as NAB goes up, that decreases H, which is what you want, but it also increases S. Sorry, decreases S, sorry. Increasing the number of AB bonds makes H more negative, and it makes S also more negative. But this is a minus S term, so there's a balance. The entropy term, it's always back to the same competition. The enthalpy term is trying to cause things to form, like pairs to form. So the enthalpy term, which is negative in this case, is trying to have short-range order with AB pairs. The entropy term is opposing. The entropy is always greatest when the system is disordered. Okay, so let me maybe rephrase it. The enthalpy term, the H term is negative in what I'm showing. That H term is trying to give you pairs, trying to make the number of AB pairs as big as possible. The entropy term is counteracting this. The entropy term is trying to have random mixing. Random mixing, and if you didn't have an H term, you'd have random mixing. So the random mixing. The random mixing term, however, becomes more important as you increase Z, because now you have more places to put the bonds, so you just have more entropy. If I'm distributing my atoms over n sites, or if I'm distributing them over 12 n sites, I have more entropy when I'm distributing them over 12 n sites. So I'm giving the entropy more weight. So by increasing the entropy, by increasing Z, I make the entropy term more important relative to the H term when you're doing this minimization. I don't know how to say it any differently. You don't seem convinced. If I had an infinite number, suppose that Z was equal to extremely high number, okay, then the system would have a huge number of sites over which to distribute the bond. So what it's going to try to do is it's going to try to become an ideal solution, because that gives you a really big entropy. Because you got your ideal entropy term times 300. So the entropy term is going to always top the short range ordering. So Z is 2 is going to give you the most short range ordering. Z is infinity gives you the least short range ordering. It gives you no short range ordering. Because with Z is extremely large, you have a huge number of places to put your atoms. The system is simply going to become ideal. And these are calculated here. So you see that by increasing the value of Z from 2 up, you get almost exactly the same effect as you get by just keeping Z as 2 and increasing the Bragg-Williams term. However, the effect on the entropy is a bit different. Okay, this is the effect on the entropy. This is with Z equals 2, but increasing the Bragg-Williams term. Okay. Z, the entropy then never goes negative because this is an exact solution. So this now is taking the Z's, increasing the Z's has the same effect on the enthalpy. It rounds it out, and it also rounds out the entropy, but what it does is it also at first brings it a little bit negative. So this was a Z equals 2, then as you go to higher Z, Z is 6, it's more rounded, but it also unfortunately has gone somewhat negative. Then it comes back up and Z becomes larger, it comes back in very soon. So this using larger values of Z than 2 has the same effect of rounding things off, but it also has this unfortunate effect of making a slightly negative excess entropy in the middle if you have a very large negative value of omega. If the value of omega is only slightly negative, it doesn't make much difference. So, however, back when we were doing most of our optimizations, this is what we did. We tended to use, well, in the oxide systems, we tended to use Z equals 2. Because these were very highly ordered systems, okay, and we didn't want a negative entropy in the middle. So if you look at our old optimizations for calcium and silica and all these oxide systems, we use Z equals 2, but we didn't use Bragg-Williams terms, we just used Z equals 2. And what we got was entropies that looked okay, but the entropy and the heat are somewhat too sharp in the middle when you use Z as 2 and you don't use a Bragg-Williams term. For many of our alloy systems, which are less negative deviations, we tended to use Z to be 6 or Z to be 12, okay, which gives you less sharp, nicer fit in terms of H and S, but does tend to have a problem. But the alloys, of course, are rarely so negative anyway, so even with Z as 2, they're higher up. They're not that far from the ideal limit. But we tended to use the Z as 6 or 8 or 12 or something like that, which gave us the rounding we wanted, and it didn't make that big a difference, but the entropy isn't quite kosher. The trouble is, if you have omega is very, very negative and you use Z as greater than 2, this really becomes quite negative here. You don't really want that, so it goes back to the you can't have everything with the thing. So that's what we did. We tend to use Z equals 2 for things that were very highly ordered, like some of the oxide silicate systems. So then you got too sharp around the middle for H and S. Or we use larger values of Z, which rounded things off, but makes the entropy a little bit incorrect. Not too much, this is not that big an effect. What we'd like to do now, though, I think if I were to do everything over again, what I would do is I would keep Z equals 2, because that's giving you the right entropy, and I would then add on Bragg-Williams terms to make the thing rounder, and then I think you're going to get the nicest fit that way. And we're doing some of that now with our oxide systems. The new oxide systems, we're putting in Bragg-Williams terms. Okay, let's stop there for a few minutes. Oh, why do I have 3? Why? What's that? Store it. So it stopped.